Now that we have thoroughly discussed the nucleus of the atom, we are now ready to discuss where the electrons are located specifically and what the importance of electrons are in chemistry. So we left off with the Bohr model of the atom, and this is that planetary model that we talked about. And in this model, we have our dense nucleus with our protons and neutrons. And then we have our electrons outside in these specific orbits. And so these electrons move around the nucleus in this model in a discrete, at a discrete distance from the nucleus. And the electrons cannot exist between levels. They can only exist in certain spaces. Now, this model was not popular for that long before Einstein and several others worked out quantum mechanics, like, Schrödinger, Heisenberg, and they worked out this quantum mechanical model of the atom. So in this model, we still have protons and neutrons in the dense nucleus, and the electrons orbiting the nucleus. But instead of a discrete energy level where we'll find them, where we will find electrons spinning in circles around the nucleus at a specific circular distance, what we actually have are these things called orbitals, not to be confused with the orbits before. And mathematical equations show that there are certain probabilities, areas of high probability for finding an electron. So we don't know exactly where it is, but the closer we are to one of these dots, or the darker it is, then you're more likely to find an electron in that region. And so it's really just about how likely are you to find an electron somewhere in space if you were able to take a snapshot and freeze an atom. And where would you find the electron? And the different orbitals will have different shapes or boundaries and energies. And the energies of these electrons are still quantized. We can calculate the energy of an electron in a certain space, but we don't always know exactly where that electron will be. So here's an example. We have a picture here of Tacoma, Washington, and we want to find TCC in Tacoma. And so the first thing we can do is narrow in using the zip code. It's a little broad, but we know we're somewhere in this region between Fircrest and University Place, and in the zip code region of 98466 of Tacoma, Washington. We can get a little closer with the street name. 19th is part of the address for the main building of Tacoma Community College. So we're narrowing in even further by adding the street name. Finally, we can do the street number, and this narrows the area even further and gets us to more or less the exact location of where we were looking. Now, we can do the same thing, and much like with an atom and an electron, the atom is a large area, and there are these boundaries which show where the electron could be, much like TCC has these boundaries here. And so we could be at TCC, we have an address, but it could be anywhere within this region. And that's what we see with electrons in atoms. So here's the electron's address. We start off with the shell, or the energy level. It is a whole number, and it increases by 1 until, well, theoretically infinity. N defines how much energy it is in an electron that is in this region. So where N equals 1 here, n equals 2, n equals 3. So this would be the first shell. This would be the second shell, the third shell, and on and on. So this is our, this is like the zip code. We're getting close, but we don't know exactly where. And you could think of the city and state as like the type of atom that it is. So is it a hydrogen or a helium or what have you? All right. So now each shell has subshells, and these all have letter names. And you don't need to memorize all of this, but I just want to show you that these letter names tell us the shape. So this is the boundary. And so within this boundary, the S looks like a sphere, and there's only one of them. Then there's the P subshell, and it is subdivided further. And then there is the D subshell, and it is also subdivided. And then the F subshell is subdivided. And you can see they increase by odd numbers. So there's 1, there's 3, there's 5, there's 7. And if we were to keep going, we would just go G. There would be 9 of those, and then H, and there would be 11 of those. So you would just kind of increase by 2. Lastly, we have orbitals within those subshells. And each orbital can hold a maximum of 2 electrons. And the larger the subshell, the more electrons it can hold. And so you can see that for the S, there was only that one orbital. And then the P subshell had 3 orbitals, so it can hold 6. The D subshell had 5 orbitals, so the maximum number of electrons it can have is 10. The F subshell has 7 orbitals, and so the maximum number of electrons it can hold is 14, and so on. So let's talk a little bit about electron configurations. This is like writing out the address for the electrons in an atom. So here we have a lithium atom. And if we have, in the first shell, there's only one subshell, and the name of that subshell is 1s, and it has 2 electrons. So if we look at our picture here, we could label this as the 1, and this one is 2. And if we look in the 1 shell, there's only one subshell, and its name is 1s. So we would write 1s, and it can have exactly 2 electrons, so we put a 2. That takes care of this electron and this electron. Now we move to our next shell, and it has it has 2 subshells. The names are 2s and 2p, and it could hold theoretically a maximum of 8. So we look here, we're in 2, and we're going to start with S and then move on to P. So we go 2S, and we see we only have 1 electron, so we can put a little 1 up here. So our electron configuration for lithium is 1s2, 2s1. And then if you want to know how many electrons it has, all you do is count the superscripts. So 2 plus 1 is 3. 1, 2, 3. Lithium has 3 electrons. So let's write the electron configuration for the next atom, beryllium. Now this is the order in which we write them. We write the electron configuration. So we start with a 1s, and then we move to the 2s, then we move to 2p, and then 3s, and then we do 3p, 4s, 3d, 4p, 5s. So this is the order in which they get filled. So first off, we have to know how many electrons beryllium has. So we look at the periodic table and we see that the uncharged normal atom of beryllium has 4 protons, so it would also have 4 electrons. And so we start with our 1s, and there are 2 of them. And then we can go 2s, and there are 2 of them. And now we're ready to stop because 2 plus 2 is 4, and we are done. Let's do one more example. Carbon. Carbon has 6 electrons in the neutral atom. So 1s, 2, 2s, 2, and now we do 2p. We have 2, 4 already done, and so we have to, how many more electrons do we need? Well, we have 2 more, so there must only be 2 of them in that 2p. It can hold up to 6, but we only have 2. So 2, 4, 6, we've got 6 electrons. So this table here kind of shows you the group and what the highest energy level is that you would fill. So with our period 1, group 1, we have 1s and 1s, and so that's hydrogen and helium, and it's full. We move down to the next level. This would be our 2, then 3, then 4. So as you move down the group, you increase by 1 digit. So that is the energy level, or the shell. The letter is the subshell. So this is the S subshell. These are S's. So we fill the 2s, 1 electron and 2 electron, and then the 2s gets full, and then 1, 2, the 3s gets full, because remember, the maximum number of electrons an s orbital can have is 2. So s orbital, 2 electrons. P orbitals now, these can have 6. So the p orbital, we can have 6 electrons, and we see 1, 2, 3, 4, 5, 6. And then we're ready to move on to 3. And again, 3s can have 2 electrons, the 3p can have 6, and then 3d can hold up to 10. So why do we care about this? Well, when an atom is going to interact with another atom in a chemical reaction, only the electrons that are in the outermost energy level can do anything. And so here we have the 1s, and it's full. And so we call these core electrons because there's another energy level out here. And so we would only focus on chemistry happening here. These electrons are too attracted to this positive 3 nucleus here to do anything chemically. So the only option for chemistry with a lithium atom is with this electron right here. And these outermost, the outermost energy levels that are occupied, that is what we call the valence electrons. So we are looking for the outermost shell, which we term the valence shell. So the valence shell is the highest occupied principal energy level, and within the valence shell are the valence electrons. So we can count the number of valence electrons in each of these. So for boron, we've got 2, 4, 5. Carbon, 2, 4, 6. Nitrogen, 2, 4, 7. 2, 4, 8. So you're probably seeing a pattern here. So we are going to practice with these electrons, and then we are going to talk about why certain atoms are more reactive than others, and it has to do with these valence electrons and how many electrons are in the outermost valence shell.